Hello, welcome to this video. The topic is conservation of energy in waves, and the essential question is, how does the principle of conservation of energy impact our observations about waves? So we got to start with remembering that wave energy is the amplitude or the height of the wave. And so as we start talking about our observations about energy and conservation of energy, what we'll be looking at is how high the waves are and whether the height of the waves is conserved, the amplitude of the wave is conserved. And we should see that it's conserved in closed systems, and we should see that it's not conserved in open systems. A reminder that high amplitude means a lot of energy, right? It takes a lot of energy to make that big wave, and low amplitude means it's going to have just a little bit of a jiggle. Amplitude is an independent variable, so it doesn't depend on any of the other variables. When we move into the other videos a little bit later on, you'll learn about other variables that we use, and they are no relationship with amplitude. Nothing you do to the wave can change the amplitude other than putting more energy into the wave pulse. Okay, so we're going to actually go through three different sort of scenarios, or three different ways that we either notice energy being conserved in a closed system or not conserved in an open system. And the first one has to do with sort of the basic observation of waves. So let's do a little thought experiment. Imagine you're holding one end of a long rope. You make a wave crest with an amplitude of 1/2 meter at one end of the rope, and that wave crest is going to go through the rope, through the medium, and hit someone at the other end. The question is, what will that amplitude be when it hits that person? Will it be more than 5 meters? Will it be exactly 5 meters? Or will it be less than 5 meters in the real world? Hopefully, if you think about it, you'll realize that that wave is going to be a lower amplitude than it started. So where did that energy go? Did we just violate conservation of energy? No, we actually witnessed a process known as damping, which is what happens when there is rubbing between the materials in the mediums, or the molecules in the medium. So as that wave is moving, trying to get through the rope, it has to stretch the little pieces of the rope against each other, and in that process they rub and they actually create thermal energy. So damping is basically an open system for energy. It's taking the wave energy as it moves through the medium and turning it into thermal energy and wasting it. You've seen lots of examples of damping in the real world, I think. For example, when you yell at somebody across a room, it's quieter the further away you are, and that's because the sound wave energy is making heat as it runs through the room. It's stretching the air molecules from each other, and it's turning it into thermal energy. There are materials that damp waves quickly, and there's materials that don't damp it very much. This picture shows like a highly damped material, right? That wave is losing its amplitude very fast. There's a lot of friction as it moves through that material, and it's sucking the energy out of the system. Other materials allow the energy to stay in the system longer, and I'll show some examples of that in just a minute. Damping is actually a super important concept for real-world engineers. And when you design anything, often you want to pay attention to how well the materials that you're using are going to dampen the waves that are relevant. Sometimes you want it to dampen them a lot, sometimes you don't. For example, if you've ever been to a concert hall, you may have noticed these big panels on the roof. The job of those panels is to reflect the waves, the sound waves, without dampening them, right? It wants to bounce them off without taking energy out of them, because it wants that sound wave energy to get to all the people in the back of the room. So when you're designing an acoustic scenario, a theater of some kinds, you want to really pay attention to the damping properties of the material that you use. On the flip side of the coin, of course, if you were trying to live next door to that horrible rock star drummer, you'd want a wall that damped the sound very quickly, because you don't want that sound to get through the wall. So you want that wall to take that sound and turn it into thermal energy so that it doesn't pass through the wall and hit your ear when you're trying to sleep. Little example from my life. This is actually a picture of a scanning electron microscope. My husband works for a company that builds these devices that can look at things the size of an atom, which is super cool. But the problem is when you're looking at something really, really tiny, if your microscope jiggles even a little bit, you don't look at the thing you thought you were going to look at. So they actually spend a lot of time and effort designing these enclosures, this cage around the microscope, so that it can dampen out all of the sound and vibrations of the world going around. Because even if a truck drives by like a street away, it's enough to make that microscope jiggle so you can't see things. So you need to have an enclosure that dampens out everything else really, really fast so that all that's happening inside is enclosed. All right. So that was open system. Interference is an example of considering sort of a closed system for waves. Now, there's no true closed system for anything in the world, but if we have a material that does not dampen very much, we see this property known as interference more dramatically. So another thought experiment. What do you think would happen if you had a single rope, but two people on the sides that both send waves at the same time? The person on the right sends a 3-meter tall wave, a crest, and the person on the left sends a 2-meter tall wave at the same time. So those waves are coming to the middle, and my question is, what's going to happen when those waves meet in the middle? Couple choices. When they meet, you're going to get a 5-meter tall wave. When they meet, maybe the big wave will just sort of win, and we'll have a 3-meter tall wave. Maybe they kind of cancel each other out, and we get a 1-meter tall wave. Maybe we have no idea, and there's some kind of crazy earth-shattering explosion. I don't know. For some reason, that's always a popular option. Well, let's take a look on the next slide and we'll see what actually happens. So when two waves meet in the middle of a medium, the amplitude of the waves will actually add up or subtract if they're on opposite sides of the wave when they meet in the middle. We sort of can categorize this into two categories, constructive interference or destructive interference. We see constructive interference when we have two wave crests on the same side of the material of the medium. And when they meet, they make a wave crest that's bigger than either of the two of them. In theory, it should be the height of the two of them added together if we didn't have any damping, right? So you see these waves are about that high, but when they meet in the middle, the resulting wave is about the sum of those two waves. Incidentally, those waves are not bouncing off each other, they're actually passing through. This is the taller wave moving to the left, and it will continue to be the taller wave, and it just passes through and keeps going to the left. And we've got the slightly shorter wave that passed through. The other kind of interference is known as destructive interference, and that's kind of a tricky name because it's not actually destroying the energy. The energy is staying in the system. These are both examples of closed systems. But in destructive interference, you have the initial wave pulses on opposite sides of the medium. And so when they meet in the middle, what actually happens is the medium sort of flattens out, or you get a smaller vibration in the medium while those waves are passing through each other. But then the waves kind of regenerate and continue on their way. Waves aren't like mass. If two people tried to run at each other, they would crash and stop. But waves are made up of energy, so they can actually just pass right through each other. So what you'll notice in this medium is if you watch about this spot where I'm putting the dot right there, you'll see that part of the medium barely moves at all. And there's actually a moment in time where the entire medium is essentially flat. And that's when the two waves have canceled out. Then that down wave on the left will continue moving to the right, okay, that way. And the other wave continues moving this direction. So just like the other example, they pass through each other. The mathematical interpretation of this is known as the superposition principle, and the idea is that you can just add up the values of the wave pulses to find the value of the wave pulse in the middle. At any instant in time, we have the same total amount of amplitude in the medium. So a couple examples, if you have a wave of amplitude 1 and a wave of amplitude 2, right, when they meet up in the middle, it's 2 plus 1, they're going to be 3, whatever we're measuring this in, tall. And we see the same thing on destructive. If I have a -1 or a +1 wave and a -1 wave, that adds up to 0. Therefore, over here at a later moment in time, we might have an instant in time where it appears that there is 0. That would be the same amount of energy. And then later on, we have the -1 and the +1, but that still adds up to the same value. So you can just mathematically add up the values of the wave pulses. The third phenomenon I want to talk about has to do with what happens when waves hit the boundary of one medium into the other. It's really an interesting situation, and it has lots of repercussions for light and rainbows and optics and all sorts of crazy things. What happens, music. The big idea is waves that hit the boundary of one medium. So when they get to the end of the medium, that amplitude splits into 3 or more small pieces. There's 3 main ones it splits into. Some of the wave energy is transmitted, and that means it goes into the new medium. You've noticed this if you had a friend outside yelling at you outside of your house, you can hear their yell. It goes into, through the house. Or if you're underwater, you can hear stuff out of the water. It goes into the new medium. But part of the wave is also reflected back. And you can hear this with sound, with an echo off of something, or even with light. If you look at your reflection in a window, you're seeing the light wave that hit that boundary and then bounced back to you. And then part of the wave is also absorbed, and it turns into waste energy through a bunch of processes, through damping, or for light, it's a slightly different process, but that wave energy still exists, it's just probably turned into a different form. So here's kind of an image showing a sound wave that is going into a piece of glass or a medium, and when it hits that glass, it's splitting. So this is the wave number 1 that's coming in, and then it splits into 1 part, 2 parts, and then 3 parts. But energy is still being conserved. That means that the total amount of energy in the system is the same. So each of these 3 parts has to be smaller amplitude than the incoming wave so that we can conserve energy. All right, so let's look at an example of how we could actually do a math problem with a boundary reflection. If we had a rope where we knew that the original wave pulse had 10 joules of energy, and then we measure the rope after the boundary and we find that it only has 5 joules of energy, and we measure the reflected wave pulse and we know that it has 4 joules of energy, then you can also figure out that there must have been 1 joule of energy that was absorbed or turned into heat or sound or something else when it hit that boundary that was basically your waste energy. All right, so let's summarize this video, and in your notes, please make sure you had good notes on this, because I'm going to ask you to submit a photograph of them. How does the principle of conservation of energy impact our observations about waves? And as always, I've got a nice Calvin and Hobbes to take you out while you write your summary. Thanks for watching.